Solutions and electrolytes going to be the topic of this lesson, and we're diving into a new chapter that's going to in large part deal with aqueous reactions. And aqueous reactions are reactions that take place in water, and that implies you have a solution. So we're going to start off by defining what a solution is at the beginning of this lesson, and then we're going to start talking about what are known as electrolytes. It turns out that water is not electrically conductive, but when electrolytes are dissolved in it, they make it electrically conductive. And we'll talk about strong electrolytes, weak electrolytes, and non-electrolytes. And then we'll polish this lesson off by talking about the solubility rules for ionic compounds in water. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. In addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You can check out those courses at chadsprep.com. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel and click the bell notification. All right, let's dive in. So I'm going to start by defining some vocabulary here. I'm going to start with solution. Solution is going to be defined in terms of its components, solvent and solute, it turns out. And so you probably have at least some vague idea of what a solution is. And most of the solutions you're ever going to deal with is where they're going to be dissolved in a liquid. And in this chapter, that liquid is going to be exclusively water. And we refer to those as aqueous solutions. All right, so the solvent is typically the liquid that everything is dissolved into. And when we say everything, well, the things that are dissolved in that liquid are called the solutes. Now, again, your solvent is usually going to be a liquid, but in principle, we have examples of solid solvents, liquid solvents, and gaseous solvents. And that gets a little confusing, but in this course, in fact, the entire year of general chemistry, you're probably only going to be experiencing liquid solvents. Now, the solute, on the other hand, though, could be a solid, a liquid, or a gas, and you're going to see examples of all three of those. Now, most commonly, you probably think of solid solutes, like dissolving salt or sugar in water, but you should know that you can dissolve a liquid in water, and you can dissolve a gas in water as well. So if you look at a typical beer might have like 5 to 8% alcohol content, and a typical wine would be right around 12% alcohol content. And my question for you is, in that beer or wine, if it's only 5 to 8% in the case of beer or 12% in the case of wine, alcohol, and that's ethanol content, then what's most of the rest of the solution made up of? Well, it's mostly water. And again, you've got some other minor components that are also solutes in there, but it's mostly water. And so in that case, water would be the solvent, and the ethanol, which is also a liquid, would be the solute. And so it turns out when you've got both a liquid solvent and a liquid solute, whichever one you have more of ends up being the solvent, and whichever one you have less of ends up being the solute. But you can also have gases dissolved in water, let's say, or any liquid. So my question for you would be, what do fish breathe? So, well, it turns out that fish breathe O2, oxygen, just like you do. And a lot of students think sometimes that they're breathing the O in H2O, and that's totally not true. They're actually breathing O2 that's dissolved in the water. And so we often write that little aqueous label there to show that. And that's why, if your fish doesn't get proper ventilation on their fish tank, or maybe if you cover up their fish bowl, if you just got a plain old fish bowl, if you cover that up for more than a couple of days, your fish is not going to be happy and probably not going to be very alive either. And the idea is that they'll have consumed all the O2 in their fish bowl, and they need more from the atmosphere to dissolve into the water. And if you cut it off from the atmosphere, that's not going to happen. And once they use up all their O2, they're done, and they're not going to get any more. All right, so you definitely can have a gas dissolved in water, and if you go into your typical chemistry lab, you'll find out that most chemistry labs have some hydrochloric acid solution. And it turns out that pure HCl is a gas, and so what you actually have in the lab is definitely not pure. You have an aqueous solution of HCl, and so just another example where we can dissolve a gas into a liquid. All right, so there's our solution vocabulary, and now we've got to bring up another term, and that term is electrolyte. All right, now we need to talk about electrolytes, and it turns out that water is not electrically conductive. This is somewhat surprising to students because they're like, Chad, I've learned from when I was a little kid that you don't go swimming during a lightning storm or you'll get electrocuted. But now you're telling me that water is not electrically conductive. Yes, that's what I'm telling you. No, I'm just kidding. Don't go swimming during a lightning storm. So it turns out that water still is not electrically conductive when it is pure. But when there are what we call electrolytes dissolved in that water, it makes the water conductive. And so it turns out an electrolyte is anything that dissociates into ions when it dissolves in water. And so not everything that dissolves in water dissociates into ions, but the things that do dissociate into ions are called electrolytes. And the greater the degree to which they dissociate into that water into ions, the more electrically conductive they're going to make that water. So it turns out your swimming pool is chock full of electrolytes because you sweat, and then you jump in and you got lovely ionic compounds, salts and stuff like that on your skin that are going to dissolve in the water. Your little brother pees in the pool. You have carbon dioxide from the atmosphere dissolving into the water, providing ions as well. There's all sorts of ions in your swimming pool, and it is highly electrically conductive, which is why you don't go swimming during a lightning storm. All right, so electrolytes are going to come in a couple of different fashions. Strong ones, which are ones that when dissolved in water dissociate into ions completely. And so those come in three types. We got soluble ionic compounds, strong acids, and strong bases. Now, how do you recognize when you've got a soluble ionic compound? Well, let's first off remind ourselves what it means to be an ionic compound, and that's usually metal and nonmetal, or like metal and polyatomic ion, or something along those lines. And so a good example here would be like sodium chloride. Now, how do you know that he's soluble? Because not all ionic compounds are soluble. Well, one, from experience, you probably know that you can dissolve table salt, kitchen salt, if you will, in water to a very great extent. But we're going to learn some rules. After we're done talking about electrolytes, we're actually going to cover the solubility rules for ionic compounds in water. And we'll find out how to predict and use those rules to predict which ones are soluble and which ones aren't. Suffice it to say, though, NaCl is a soluble ionic compound and is therefore a strong electrolyte. All right, strong acids are the next ones. And how do we recognize we have an acid? Well, you might recall back from chapter 2, we also learned that acids begin with an H. And it turns out, as far as the ones that are strong, the ones that are going to dissociate into ions 100%, there are 7 of them. Some people only put 6 on their list. We're going to put 7, and I'll tell you which ones some people don't include on their list. But your strong acids include HCl, HBr, HI, HClO4, here's the sometimes one, HClO3, H2SO4, and HNO3. Those are the 7. And again, this HClO3 is kind of the sometimes strong acid. Some people do include it, some people don't. Go with whatever your textbook or instructor is going with. But here are the 7. And the way this works, not only do you now know the strong acids once you memorize these, and you do need to memorize those, but now you can recognize the weak acids as well, because anything that starts with an H and is an acid, therefore, but is not one of these, would be by default a weak acid. So if I say HF, you'd be like, well, it starts with an H, so it's an acid, but it's not on the list, so it's not a strong acid, it's weak acid by default. NO2. Well, HNO3 made the list, but HNO2 didn't make the list and would be a weak acid by default. Okay, so now we know our strong acids. So we've also got a variety of strong bases, and your strong bases are things like NaOH. And it turns out all the strong bases you're going to learn here are going to be hydroxide bases like NaOH, and it turns out it's going to be most of the group 1 and group 2 metal hydroxides. All right, so here are your group 1 metal hydroxides: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. You might be like, well, Chad, what about francium hydroxide? Well, francium's super radioactive, doesn't stick around very long, so nobody plays with it. But if we did, it would be a strong base as well. And if I said strong acid, I meant base. And then your group 2s, the biggest ones are also on that list: calcium hydroxide, strontium hydroxide, barium hydroxide. Notice magnesium really depends on who you talk to. Some people do consider it a strong base, some people don't. And the truth is, I don't actually consider any of these to be the strongest of bases, like the ones in the for the group 1s, because these aren't the most soluble things in water. But to the degree that they are soluble, they do dissociate into ions completely, and so most people class them as strong bases. But magnesium hydroxide usually doesn't make people's lists. Cool, so there's how you recognize strong electrolytes. It's either a soluble ionic compound, and again, we'll cover those rules in a little bit. It's one of your 7 strong acids, or one of your group 1 or 2 metal hydroxides here for your strong bases. Your next type of electrolyte is going to be weak electrolytes. And your weak electrolytes are going to come in one of a couple of varieties as well. And usually the ones you're going to see are either weak acids or weak bases. That's the way that's going to play out. And so how do you recognize a weak acid? Well, again, any acid that is not strong. So again, if I give you something like HF, it begins with an H. It's not on that list, so it's an acid that's not strong, i.e. it is weak. But I do want to put one other type on there. So this guy right here ends with this COOH, sometimes written as CO2H, same diff. That's an example of what we call an organic acid. You'll learn about them more in organic chemistry if you get there. And this is the one acid you need to recognize that doesn't begin with an H, but we end the formula with an H. And it's important that it's COOH, that it ends with that term. Now, what's at the beginning here is not so important, but when it ends with a COH, that's another example of a weak acid. And again, one you're on the hook for, even though it doesn't begin with an H. All right, so weak bases, on the other hand, these are much more difficult for us to give you a comprehensive list here. So what I'm going to give you is ammonia. And things that look somewhat similar to ammonia are going to be your weak bases. And so in this case, we got ammonia and maybe something like methylamine, it turns out is the name there. But instead of, on nitrogen, one of the hydrogens is replaced with this CH3 group. And so typically the weak bases you're likely to encounter are going to either look like, be ammonia or look somewhat similar to ammonia with a nitrogen. But it's not as easy for us to give you a whole bunch of weak bases to recognize like it is with the weak acids. The weak acids, I have dozens and dozens I can give you because you just have to know that it's an acid that wasn't on the strong acids list. All right, last class we've got to talk about are the non-electrolytes. And non-electrolytes might dissolve in water, but they don't dissociate into ions when they do. So, and your non-electrolytes, the way you want to recognize them is they're not acids, they're not bases, and they're not ionic compounds. So they are molecular compounds, so made of all nonmetals, but not acids or bases. Notice acids are typically made of all nonmetals. These lovely bases are over here, these weak ones anyways, are made of all nonmetals. But they are weak electrolytes, in this case, weak acids, weak bases. The non-electrolytes, therefore, are the rest of the molecular compounds. So for example, this is methanol. It is all nonmetals. And a lot of students are like, oh, Chad, whoa, it ends with an OH. Well, it doesn't end with a COOH. And so it turns out this is an alcohol, not an organic acid, and is a non-electrolyte. You can dissolve it in water, and it does not make that water electrically conductive because it does not dissociate into ions to any significant degree. Another good example would be sugar. And technically, this is glucose, not sucrose, which would be the sugar you have at home in all likelihood, but this is glucose. So, but you're much more likely to see this, but notice it is made of all nonmetals. It is a molecular compound, and even though glucose is highly soluble in water, dissolves in water, it does not split apart into ions. It does not dissociate into ions, and is therefore a non-electrolyte. And so now we know how to recognize strong electrolytes, weak electrolytes, non-electrolytes, and say you put an equal concentration of a strong, a weak, and a non-electrolyte in water, the strong electrolyte solution would be the most electrically conductive, then followed by the weak electrolyte solution, and then the non-electrolyte solution should still be not electrically conductive. So now we're going to move into talking about the solubility rules for ionic compounds in water. And most of the time you're probably just going to call these solubility rules, but it is specific to ionic compounds and where the solvent is water. We can actually talk about solubilities and a lot of other things. So, and it turns out we're going to just put two classes on this. We're going to put soluble and insoluble. And what the truth is, there's really just a whole range of solubilities, up to really, really, really soluble to really, really insoluble and everything in between. And we just draw a line in the sand right in the middle. So, and it's a little bit arbitrary where we put that. So, but somewhere probably in the ballpark of like 0.01 molar in some books, or 0.1 gram per 100 milliliters, or, there's a slightly different place where we put it. But anything that's more soluble than that, we're just going to call soluble. And anything that's less soluble than that, we're just going to call insoluble. Now, one thing you should know is that even for the things we call soluble, they're going to reach their limit. You can, pour them in water, and at some point, they're not all going to dissolve. So the same thing is true on the other end for things that are insoluble. Just because it's insoluble doesn't mean it doesn't dissolve at all. It means it's only going to dissociate and dissolve maybe a very, very tiny extent. Cool. And like I said, there's varying degrees of solubility, and some things are more soluble than others. And we'll actually treat with that, treat the varying degrees of solubility in second semester general chemistry, both, a little more mathematically and stuff. But for now, there's just two categories: soluble and insoluble. And you've got to be able to recognize them based on using some solubility rules. And so we're going to start and we're going to classify this based on the anions here. And by looking at the anions, you can kind of get an idea of whether or not something's going to be soluble or not. And so it turns out, nitrate, acetate, chloride, bromide, iodide, and sulfate, if you're a salt with one of these ions, you are in all likelihood going to be soluble. But there are some exceptions for some of these. So like if we look at here, this is sodium acetate, and acetate, it can be written CH3COO, but I also wanted you to see it written like this with CH3CO2. And it turns out that all acetate salts are soluble, no exceptions. So it's true for nitrates and acetates. And so if you ever see anything with an acetate or a nitrate, it is automatically soluble. Done. Don't even have to care who the cation is, because there are no exceptions. Now, if you look at chloride, bromide, and iodide, on the other hand, most of the ionic compounds that have one of these are soluble, but there are exceptions in silver, mercury 1, and lead here. So in this case, I see magnesium chloride, and magnesium is not on the exceptions list, so this is indeed soluble. But the next one has mercury 1 in it. It's mercury 1 iodide, and so it's going to be insoluble. Usually you're an iodide salt, you're probably going to be soluble, but not for silver, mercury, or lead here. All right, last one, we're going to look at a couple of sulfate salts. And in this case, most sulfates, again, are soluble. They're typically soluble. So except for these guys, they're the insoluble ones. So, well, potassium's not on that list. So potassium sulfate here is going to be soluble. But barium sulfate, on the other hand, is one of the exceptions and is therefore going to be insoluble. Now, it turns out I'm giving this to you, one of the commonly represented ways where the solubility rules are organized by anions. However, sometimes you'll see people give you some rules based on cations, and they'll say, well, all group 1 metal salts, and that means lithium, sodium, potassium, rubidium, cesium, they're all soluble. And that's true, but I'm organizing it by anion instead, which is a common convention. You'll also sometimes see that all ammonium salts, NH4+, are soluble as well. And that is true, but it's not part of the convention I'm going to use here. Okay, so these are the anions associated with soluble ionic compounds for the most part, with a few exceptions for the halides as well as for sulfates. Cool, this is also not an exhaustive list, just an FYI. It's just a commonly presented one in a lot of textbooks. Okay, so here we're dealt with the mostly soluble anions, and now we're going to switch gears and deal with the mostly insoluble anions instead. All right, so this is the second half of our solubility rules for ionic compounds in water. And whereas the first half of the rules, again, dealt with the anions that are mostly associated with soluble ionic compounds, now we're going to have a set of anions that's going to be mostly associated with insoluble ionic compounds. And so if you see sulfide, carbonate, phosphate, or hydroxide, you should be thinking probably insoluble. Now, you might be thinking, do I have to memorize these rules? Well, that actually depends on your instructor. If they have you memorize them, my apologies. And if they don't, great. I would say about 50% of the classes, usually these are just provided for you. You can look them up in your textbook, or they'll be given on the back page of an exam or something like that. And the other half, unfortunately, they do make you memorize some cursory solubility rules. My apologies. All right, so ask your instructor which of those two groups you fall into. All right, so first thing we should notice, like when we see sulfide, again, sulfides are notoriously insoluble. And so you should think, oh, sulfides are probably going to be insoluble. But the exceptions include ammonium, group 1, which again, lithium, sodium, potassium, rubidium, cesium, and then some of the group 2s here, calcium, strontium, and barium, some of the bigger group 2s are the exceptions and would be soluble. So if we don't have the exceptions, like here we've got copper sulfide, then that's definitely going to be insoluble. But now when we have an exception, like with ammonium here, now the exceptions are going to be the soluble ones. So in the last set, we had the mostly soluble compounds, and the exceptions were insoluble, but now we have the mostly insoluble compounds, and the exceptions are the soluble ones. So same thing here with carbonates. Most carbonates are insoluble. The exceptions are either ammonium or group 1. But the group 2s, like calcium, are still insoluble. They're not the exceptions. But sodium is a group 1 metal, and so that's the exception and is now soluble. Same thing, if you notice phosphates match up with the carbonates. They're typically insoluble except for ammonium and group 1. And so in this case, barium phosphate is indeed not on the exceptions list, so it's insoluble. So, and life is good. And then finally with the hydroxides here, most hydroxides are insoluble except ammonium, the group 1s, or the largest group 2s, same as we saw with the sulfides here. And so manganese hydroxide here is not on the exceptions list and is insoluble, but potassium is a group 1 metal, and so is definitely one of the exceptions and is one of our strong bases as well, and is soluble. Cool, that's how you use those solubility rules. And again, half of you, you're gonna have these solubility rules handy when you need them. And the other half of you are gonna have to memorize some version of solubility rules, probably fairly similar to what we've presented here. Now, if you found this lesson helpful, that like button lets YouTube know that they should be sharing this lesson with other students as well. And if you've got questions on the lesson, feel free to leave them in the comment section below. And if you're looking for practice, either quizzes, chapter tests, practice final exam rapid reviews, check out my General Chemistry Master course at chadsprep.com. I'll leave a specific link in the description below. A free trial is available. Happy studying.